Hi, everyone, and welcome to February 2025's A3D3 Seminar. I'm very pleased to be able to introduce our speaker today, who's Professor Jess MacIver at the University of British Columbia, Department of Physics and Astronomy. Jess holds degrees from Syracuse University and the University of Massachusetts Amherst, and she was previously a postdoc here at Caltech. She's one of the leading experts in gravitational wave gravitational wave astrophysics, and she was a member of the LIGO team since 2007 and was part of the team who detected the first binary neutron star 170817, which won the Science 2017 Breakthrough of the Year prize. Her work focuses particularly on detector noise characterization, calibration, and multi-messenger astronomy, and she's going to be talking today about the application of machine learning in this exciting environment. Jess.
Thank you, Matthew. So great to be here. And I see some other members of the same team are also online. So hello to you as well. So I'll be presenting today on behalf of the GWSkyNet team, which is led by a postdoc here at UBC, Dr. Mervyn Chan, in collaboration with the PhD students at McGill, Nair Raza, Daryl Haggard, also at McGill, and Ashish Mahabal, who is at Caltech, in addition to dozens of people, some of whom are listed here, who have all contributed to bringing GWSkynet to production run. So we'll learn more about this machine learning algorithm in a minute. But all credit should go, I think, to Mervyn when we get to a detailed description of the performance of the algorithm, and Neuer when we start to talk about explainability. So I want to back up and give you a big picture overview of what gravitational waves are, since they're quite a bit different from particle physics or other areas of astrophysics. So the general idea, everything that you need to know about general relativity to understand a gravitational wave, is that we've got some source, it's got some asymmetry of its quadrupole moment, so it's some asymmetry of its distribution of mass and energy. So that could be two objects that are circling around each other that break spherical symmetry. Maybe that's a nearly spherical object with some kind of deformity that's spinning. There are many ways where one could produce this quadrupole moment changing over time. And when I have such a source, so its dynamics are going to be encoded in the gravitational wave signal emitting from it. So here on the left-hand side of this equation, we've got the amplitude of the gravitational wave strain over time, and this is proportional to a very, very, very small number, which already gives you an intuition for how difficult this problem is, times the second time derivative of this quadrupole moment. So again, this is encoding the dynamics of what the source is doing, times this really important factor, which tells me that the amplitude of my signal at the source, or between the source and me, the observer, is actually going to go as 1 over r. So unlike, let's say, if you're in the business of using telescopes to count the number of photodiodes in some area, the strength of your signal will go as 1 over r squared. Here, since we're directly sensing the amplitude of the wave itself, our amplitude is going to go as 1 over r. And if I have a good model for what the source is doing, I can actually directly infer the distance to the source from the amplitude that I'm observing at my detector. So that's a really powerful tool for astronomy. And let's do a little bit more intuition building. So here, let's say we've got two black holes. Now, color here is the curvature of space-time. So we're looking at a gravitational wave source through a lens of space-time as these two black holes are orbiting around each other. And this trace at the bottom in blue, this is tracing at the amplitude of the gravitational wave that's being emitted from the source. So we can see the two black holes, they're orbiting around each other, they're radiating energy in the form of gravitational waves, which is driving them closer and closer together. So the amplitude of this gravitational wave is going to get higher and higher frequency and amplitude until finally these two black holes get close enough to start to merge. So this is the peak of the amplitude here for the gravitational wave signal, and then this new larger mass black hole is going to ring down like a bell, and this whole signature of the in spiral, the merger, and that ringing down is going to propagate at the speed of light. out into the universe in 3 dimensions. So, knowing this, we can consider how is that gravitational wave going to impact space-time as it's passing through the Earth or whatever you would like to use to sense such a wave. So here again, we've got the source, whatever that is. Maybe it's 2 black holes orbiting around each other. Maybe again, it's some kind of deformed near sphere that's spinning, but you have some source. It's got some quadrupole moment. It's producing some signature of amplitude of gravitational wave strain. And if that gravitational wave were coming into or out of the screen, it would be doing something more or less like this. So here we're seeing this perpendicular stretching and squeezing effect. There are actually 2 different polarizations of this, but we can simplify it to one for now. And if we would like to sense this kind of orthogonal stretching and squeezing, we can use something even as simple as an interferometer. So here we've got a nearly classic Michelson interferometer where we've got coherent laser light that's entering the interferometer, split by a beam splitter 50% in 2 perpendicular directions. And here it's actually circulated in 4-kilometer long arms. And any difference in the distance between these 2 mirrors and between the 2 arms, we will sense as a change in phase of the light. So we're actually going to be able to measure directly the gravitational wave strain induced by passing gravitational waves through this interferometer. And it's not quite so simple in reality. So here, just to give you a sense of the scale, so here's drone footage where we're looking back towards the building housing the laser and the beam splitter and the photodetector. And here now we're looking down at the end of the arm. So you can't even quite see the whole detector even with a drone. In the first view, we were actually looking about over half of it. So there are 2 4-kilometer long arms, and then again, perpendicular in each of those 2 directions. And they're quite sensitive. So in order to sense these ultra small effects, gravitational waves have to be able to sense relative changes in length on the order of about 1,000 times smaller than the diameter of a proton. So here's a 2-scale sense of how sensitive the LIGO detectors were just after the first discovery of gravitational waves back in 2015. And we're doing a factor of 2 or more better now today than we were back in 2015. But as you might imagine, when you have a detector that's so sensitive, it doesn't take much to move the mirrors around a little bit and introduce noise into your detector. And we have a network of these detectors. So I mentioned there are multiple LIGO detectors. So there's LIGO Hanford, which is fairly close to me here in British Columbia and Washington State in the US. LIGO Livingston, which is down in Louisiana. Both of these are 4-kilometer long detectors. We have our sister detector, Virgo. That's a 3-kilometer long detector near Pisa in Italy. That's also now participating in the current observing run, which is O4. And this network of 3 detectors was also the network that contributed to the most recently completed observing run, which is O3, where a lot of the results that you may have read about have been drawn from. And it's worth also mentioning that there's LIGO India that's being constructed. This would be another 3rd 4-kilometer long LIGO detector in the middle of India, as well as KAGRA, which is an underground cryogenic detector in Japan, and GU600, which is a 600-meter detector in Germany that's pioneered a lot of the critical technologies that we use. All right, to give you an overview, so if you've heard of the Nobel Prize winning detection from 2015, so this is a snapshot of the LIGO data from that event. It came actually just before the planned start of this observing run. So we had taken some data before at a reduced sensitivity. We took 5 years to upgrade the detectors until we were ready to start this next observing run. And we got this very clear signature in LIGO Hanford and LIGO Livingston of 2 black holes, roughly about 30 times the mass of our sun, merging. And how do we tell that they're roughly 30 times the mass of our sun, or 29 and 36 times the mass of our sun is our current best guess? So we use Bayesian source property estimation, where you assume that your data is a sum of your gravitational wave signal as seen through the lens of your detector network, plus some detector noise. And the key assumption that we use in defining the likelihood for this Bayesian approach is that this detector noise is Gaussian. So we expect when we subtract a signal, well modeled by general relativity, from our data, that this detector noise n is going to be consistent with Gaussian noise. And this has produced a lot of really interesting results. So just to give you a sense, so here are some results from some of the first two observing runs, three observing runs. And you can see that in terms of how quickly these systems are spinning and how heavy they are by this reduced mass measure called trip mass, there is some power to constrain, even from these earlier observing runs, really interesting physical systems. And we can even constrain the individual spins. So here we're looking at the two objects. This is the heavier black hole. This is the lighter black hole. Where 0 is consistent with not spinning, 1 is maximally spinning, and 0 degrees is aligned with the orbital angular momentum of the system, and 180 degrees is anti-aligned. So even from early data, we do have some power to constrain, but then there's a lot that's left unconstrained so far, where as we get more and more detector sensitivity and increase our signal fidelity, we'll be able to constrain more and more about these systems. But there's a big caveat in that we currently require this to be true. And as you will see, not all our noise is Gaussian. We do have a high rate at times of highly non-Gaussian noise called glitches that can interfere with the accurate source property estimation of true signals and introduce false positives that can complicate the process of looking for electromagnetic counterparts to these sources. So I mention electromagnetic counterparts in part to motivate one of our more famous cases. So here's a detection that was made in 2017. Here again, you can see data from the two LIGO detectors and also the Virgo detector. And you can see these much, much longer sweepings of a gravitational wave signal from the merger of two neutron stars. And this is a particularly interesting event because with those three detectors, we were able to constrain the sky map enough that partner astronomers actually could find an electromagnetic counterpart. So let's see what this looks like. So here we've got a sky map that's based on the timing between the Fermi and integral satellites. Here we've got a sky map from Fermi itself. And here this double banana in green, that's just from the two LIGO detectors. And if you add in Virgo, the third detector, then you can really dramatically constrain the sky location. And remember that we're also getting distance from gravitational waves. We get that direct estimate of distance, so it's actually a volume. And within that volume, astronomers can target particular galaxies. And then here's a zoom in of the host galaxy of the source, which is NGC 4993. So these sources are really, really rich with a lot of very interesting science. You can use the redshift from the host galaxy along with the distance as measured through gravitational waves to get this independent measurement of the Hubble constant. You can learn more about jet physics. You can learn more about the production of heavy elements. You can do tests of fundamental physics in terms of the speed of gravitational waves and light. So there's a lot of really interesting and rich astrophysics in these sources, so they're really prime candidates for multi-messenger astrophysics with gravitational waves, with light, and possibly even neutrinos. All right, so what have we learned so far from gravitational wave measurements? So here we've got mass on the y-axis of known compact objects versus distance. So green is a black hole with mass estimated electromagnetically. Purple is a neutron star with mass estimated electromagnetically. Generally, these are in some kind of a binary system. And then each one of these blue dots is a neutron star or a black hole with a mass measured with gravitational waves. So you can see a totally different population emerging, especially for these heavier mass black holes that were not detected within our own Milky Way. And you can also see we've got a population emerging in terms of gravitational waves being found completely outside of our galaxy. So we're exploring really, really new territory with gravitational waves, and it's unlocking a lot of really interesting science. So we've mentioned the Hubble constants. We also get this very unique insights into the highly dense matter of neutron stars. We can do new tests of general relativity in this really extreme space-time curvature of those lower mass black holes. And we're also starting to see gravitational waves dominate what we understand about the nature of stellar remnants, and which is driving some of what we know about stellar evolution. So where are we right now? So I told you about some detections in the first observing run. The neutron star merger happened in the second observing run. I've given you a taste of what we've seen in the third observing run. Right now, we are in the middle of the fourth observing run, which is going to run through fall of 2025. The two LIGO detectors joined with improved sensitivity relative to O3 in May of 2023, and Virgo joined in the spring of last year. So we've already taken quite a lot of data. For the LIGO detectors, a number of improvements were made, including more power in the arm cavities, baffles to combat stray light noise. So this is especially important for mitigating scattering noise, as well as some improvements to light squeezing and the test mass mirrors themselves. So what does this gotten us? So if you compare what we had seen, so these are confirmed detections from the first three observing runs, which had just over 2 years of collective observing time, to what we've seen so far in 04. So nearly well, we've got many more candidates per unit of the same time in 04. So our rate has definitely increased thanks to our increased detector performance. I'm getting alerts on my phone probably about once every few days. So we've definitely entered the regime of the high rate of gravitational wave detections. And this is in thanks, in large part, to increased sensitivity for LIGO Hanford, that's in red. So this is the angle averaged range of detection of binary neutron star mergers. We can see orders of magnitude farther for massive black holes. Blue is for Livingston, purple is for Virgo, which has been very important for constraining sky locations for signals that we have seen. And something that you might remember from earlier is that in order to constrain the sky location for the binary neutron star merger that was also detected in concert with light, we needed 3 detectors. So our duty cycle, or our duty factor for the detectors being online and taking data, is very important. We want this triple interferometer time to be as high as possible. So I'll talk a little bit about the challenges here and how this relates to this tricky non-Gaussian glitchy detector noise. But I just took a snapshot of this earlier today. So far in 04, we have almost 200 candidates that are not retracted. And we also, for the first time now, are releasing these low significance candidate detections. So over 3,500 of these as well. And this is all, again, since about May of 2023. So let's see if we can understand the duty cycle a little bit better and why this is important. So here, this is over a time scale of weeks from the start of the run for LIGO Livingston. And you can see observing mode time, and then you can also see this categorization of different, let's say, environmental states when the detector is not taking data. And I want you to notice a couple things. So in this period here, where the environment noise is preventing us from getting that green time, that uptime that we'd want to have. So this is related to this microseism noise. And generally this happens seasonally every winter. We start to see more microseismic activity that's due to the Gulf of Mexico and Atlantic Ocean starting to resonate with larger waves. We also see this in the Pacific Ocean, so Lago Hanford is not immune to this, even though it's a little bit further from the shore. But it can get very difficult for us to take data because as the ground moves, it gets very hard to keep that light in resonance in those 4-kilometer long cavities. I also want to point out here, towards the beginning of the run, we had a big dip in observing mode time for Livingston, and this is actually related to something that's marked as logging. So something that you might have noticed in that drone footage is that the LIGO Livingston detector is surrounded by trees. You may also have noticed that some of those trees are now missing. So the foresting company that works around the detector has a cycle where they'll grow the trees, and then they'll come down and cut them down. And I just want you to imagine using this Google Maps image where you think maybe the worst possible place for logging to be would be if you were trying to take a lot of data during an observing run. And then I'll show you where it actually was, just tens of meters away from the control room, um, sometime near the beginning of this current observing run. And you can actually look at the ground motion trends. So this is the amplitude of the ground motion. Near the corner station is the start line, and the two end stations are blue and orange. So you can see just at about the start of the workday, the microseism spikes, and what we lose lock. This means that we're losing the light resonance in the interferometer and its various optical cavities. And you can actually watch the interferometer try to reach this lock state again, where you can lock each of the cavities in sequence until you arrive in the full observing mode. So we try that for a number of hours, and then we give up and we're in a down state. And then as soon as that microseism drops, then we can make our way back up to observing mode. So unlike telescopes where you have to worry about clouds and dust and, whether the sun's in the sky for some telescopes, for gravitational wave detectors, we worry about ground motion. We worry about earthquakes. We worry about human-generated noise. We have some very sophisticated technology that's isolating the interferometer from some of this ground motion, but sometimes it's just a little bit too much for us to overcome. And it also introduces transient noise. So elevated ground motion can introduce these bursts of power in the data. So what we're looking at for right here, this is 1 day's worth of data, and this is frequency versus time, and the color is telling us about the signal to noise ratio, or the loudness of a glitch in the data. And I want to zoom in and just show you what's happening here in this frequency range of about, let's say, 20 to 45 or so hertz, which is right in the peak range of where we would expect to see really interesting gravitational wave signal. And each one of these dots actually corresponds to a burst of gravitational wave power like you see here. So this is called a light scattering arch. And it can be, if the ground motion is elevated, that these are happening about once every other second. So they're very, very frequent in rate, and then a gravitational wave signal would come sweep over this, also rising in frequency, so they can actually trick our searches into finding a good match with a match filter template predicted by general relativity in the same way that you would expect, let's say, a compact object merger. And then something else that I want to mention, so this is in the context of these alerts, where we have open public alerts that there is a candidate, it's got some false alarm rate that's called FAR, it's got a sky map, it's got some probability that it's assuming that it is a real signal, that it's associated with some source or another. And so here are some examples of retracted events in the previous observing run. So here's one that was predicted to be a binary neutron star, one in the gap between neutron stars and black holes, or a purported or theorized gap, and then one that was found to be consistent with a neutron star black hole. And I want you to notice that all of these alerts were retracted, but not before there was some telescope time invested in following them up as promising candidates. And there's also another class of these kinds of sources that are consistent with noise, so those bursts of glitch power in the detectors. However, they were not retracted because the false alarm rate was quite high. So the false alarm rate was more or less consistent with noise, and they were thought to be terrestrial, so they went unretracted, but they were not validated in the eventual catalog of confirmed sources. So something that would be very nice and useful for astronomers is a way to quickly and accurately tell which of these sources are consistent with noise and which of them are consistent with gravitational waves. And I'll give you one more example. So this is from this current observing run. So this is S240422. So this was predicted to be potentially a neutron star black hole signal, so consistent with an NSBH. It was fairly nearby, so on the order of 100 or a couple hundred megaparsecs. The sky location was very well constrained also, but it was eventually updated to no longer be considered significant. But this update didn't come until 72 days later. So almost 2.5 months later, the collaboration updated our knowledge of this event to be on the side of more consistent with noise. And here's where GWSkyNet comes in as a very, very useful tool. So it's a rapid signal versus glitch classifier that leverages a convolutional neural net, and it intakes the sky map information, which encodes the coherence of the gravitational wave signal across the gravitational wave detector network, and issues a score, where that score, if it's closer to 0, it's consistent with noise, and a score close to 1 is consistent with a gravitational wave signal. And because it intakes the sky map, which is a product that's issued by all of the various pipelines that run online, it's consistent across all the pipelines. So unlike, let's say, maybe the way that a false alarm rate might be computed across different match filtering pipelines, a GWSkyNet score can be compared across all of our different events. And I'll give you an example of how it works. So here's an example alert from a previous observing run. We've got the probability that this thing is a binary neutron star is 63%. The false alarm rate is 1 in about roughly 2 years. It was not confirmed later as a true event. It was also not retracted, and GWSkyNet predicted this within seconds, that this is an event that was more consistent with detector glitches or noise. And here's the input that it takes in. So you've got the volume rendering in 3 different views. You've also got the 2-dimensional sky map, as well as some other information about the detector network. So which of the detectors were online at the time, as well as the normalizations that will tell GWSkyNet how to interpret essentially the values of things like distance. How does it work exactly? So here is a map of the convolutional neural network architecture. So here's the input sky map. So here we've got one image. Here we've got the 3 volume images. And then here is it intaking the different information about the detector network configuration and also the normalization factors that it gets from the sky maps. And this is a prototype that was led by Miriam Cabrero, and that was first trained on simulated signals and glitches identified by this other convolutional neural net that's famously successful called GravitySpy on O2 glitches, as well as sub-threshold candidates. So this is a paper that was published in 2021 with the prototype, and it was very promising. However, when you add this additional detector of Virgo, it didn't perform as well. So in order to prepare this pipeline to analyze O4 data with the addition of Virgo as another detector expected to come online, so we initially started training on public O3 data, and then we did a fine-tuning with proprietary data. This is a mock data challenge internal to the collaboration, which brought this curve. So here you've got a series of 4 curves. Solid curves are these 3 detector networks. So for example, 2 LIGO detectors and Virgo, and then the dash curve is a 2 detector network. So for 2 detectors, the model is fairly consistent before and after this change, but for 3 detectors, the model got a big boost to performance. So we have done all of this training with O3 data. It's not retrained or fine-tuned with O4 data. So GWSkyNet, as it's currently running, is a machine learning algorithm that was fully leveraging data that's currently public, with the exception of this mock data challenge that leverages some of those simulated signals. And how well does it work? So for signals that are consistent with binary neutron stars, neutron star black holes, and binary black holes, it does work very well. So here's some confusion matrices for each, where it's ground truth versus predicted value for glitches and gravitational wave events. And if you're worried that you're not seeing these numbers approaching 100, so let's say that if you're in the market to find a kilonova from a gravitational wave source, you probably don't want to run the risk of missing any of those signals. So we also issue, in addition to the score, this false alarm probability and false negative probability. So this allows you to map this GWSkyNet score, so that's a score between 0 and 1, to your level of assumed risk. So for example, let's say I want to set a score threshold of 0.84, where I'm only going to follow up sources that have a GWSkyNet score of higher than 0.84, where these two curves will cross. So that means that I'm going to reject 86% of noise at the potential risk of missing 14% of signals. And I can actually scale this number, this score thresholds, for my level of risk tolerance. So let's say I'm only willing to miss maybe a few percent of possible signals. I would still, with GWSkyNet, be rejecting about 50% of noise. So if you're interested, we've got a public output guide that can help guide you to tune this information, which is publicly available right now through GraceDB for your purposes if you're interested. And just to give you a sense of how well it's performing now on O4 data, so here we have a GWSkyNet score versus this traditional measurement of whether or not the signal is consistent with a terrestrial source or an astrophysical source called p-astro, where again 0 is consistent with a glitch and 1 is consistent with an astrophysical signal. So if you compare GWSkyNet to this traditional p-astro method and look at the retracted events, GWSkyNet is doing a better job on the whole of predicting these noise events that are later found to be retracted. And some of these that are more on the edges here, so we'll wait for our single source of truth, which will be the next gravitational wave catalog, to tell which one of these algorithms was closer to correct. Interestingly, those sources that are more consistent with burst sources or identified by coherent wave burst, the BBH search, both of these metrics are fairly consistent, and they're also fairly consistent for the majority of sources. But coming all the way back to this initial example where we had a 2.5-month-long wait for an update on this probable neutron star black hole candidate, GWSkyNet actually predicted that this was a noise event very quickly, within seconds. It was not available at the time, at least publicly, at the time of this event, but GWSkyNet scores are publicly available now. So if we had a similar event in the future, the GWSkyNet score will quickly identify equivalent events as consistent with noise in almost near real time as soon as the sky map is issued. So this brings us to a journey that we, the GWSkyNet team, have been taking to try to understand why these algorithms, GWSkyNet in particular, works as well as it does. So we're here in the range. So if you look at the graph of human understandability versus model complexity, we're operating here in the deep learning regime, where it can be very, very difficult to intuit on the whole, or for any particular example, why an algorithm has made the decision that it's made. So I'll take you on a tour of our winding road to try to understand this a bit better in partnership with the neuroscientists and computer scientists at the University of Laval and cosmologists at the University of Toronto. So first I want to introduce a cousin algorithm of GWSkyNet, which is called GWSkyNet Multi. So the two students that are shown here, so this is Eitan and Thomas from McGill, decided to think about what can we do with open public alerts. Maybe we can do more than just differentiate between a glitch and a signal. Maybe we could take a likely signal and try to tease out whether it might have a neutron star in it or whether it's a binary black hole merger. So try and get a little bit more information in terms of what's going to be interesting for astronomers. So they did this test, and unsurprisingly, when you do something very similar, so glitch versus all, this algorithm has a pretty consistent performance with GWSkyNet, the original version, so that's fine. But something that really surprised us initially is that it also does a great job differentiating between a neutron star or something that might have a neutron star in it and a binary black hole, which you would not normally expect to be electromagnetically bright. So this we consider to be a mystery and a puzzling one and a slightly troubling one in the sense that you never want to feel like you don't have a rough idea of why your machine learning algorithm is making really good decisions, even when it's making the predictions that are close to reality. So our first approach, we just tried to do something out of the box. We said, okay, we've got images, we're working with images. What are computer scientists doing to try and explain algorithms that are leveraging images? So we tried GradCam, we tried Lime. Those gave us maps that said, yes, the algorithm is looking at the parts of the sky map that make sense for it to be looking at. So that was a little bit of a bust for us in the sense that there's not really any new insights in trying out of the box approaches. So here is where our partnership with the folks who think a lot more about machine learning, especially in the context of computer science and neuroscience, helped us to develop our own custom explainability methods that were really helpful. So what I'm showing you here, so here's an original two-dimensional sky image, and then here are a series of variations that are made to the image where you shrink the area, you expand the area, you scramble the image, you give it some kind of a uniform or zeroed image. This is a study led by Nayaraza at McGill. And then you watch how the output changes for various different metrics. So here's one example. So this is an uncertainty size scaling factor for distance, or for SkyMap area, rather. So here's the change in response for the GWSkyNet multi-score for whether or not this source is consistent with a glitch or an astrophysical signal. And as the scaling factor gets bigger, so as the area of the sky map gets bigger, this change becomes more and more consistent with a glitch. So this is not surprising, but it did help us to feel confident that this approach could yield some useful information. And in fact, it definitely did. So here we have the exploration of distance, where we have a perturbation scaling factor. That means we're increasing this distance term that comes into GWSkyNet multi through that same normalization set of constants. And then looking at the mean score change, so we don't see a big difference in glitch sources, but when you start to include sources that include a neutron star, when the distance goes down, it becomes more consistent with a neutron star. When it goes up, it becomes more consistent with a black hole. And you can also see a very similar mirror trend for binary black holes. So our algorithm was actually doing something very sensible. It was honing into the fact that it's not possible for us to see neutron stars far away. And because binary black holes on the whole have a lower rate astrophysically, we're going to tend to see them farther away from the Earth. So this was a mystery solved, and this gave us a roadmap for weaving in this explainability to help build trust in our users. So we found not enough to just show good performance or consistent, reliable performance. If you're doing something so high stakes, where you're trying to find a kilonova with a really low rate of candidate events, you want to be absolutely sure that you're going to use the best information possible. So this kind of an explainability study to demonstrate that the algorithm is making good, well-founded choices that we can gain some intuition for, we think is going to be really helpful for building up the user base for these tools. I also, just in the last few minutes, want to mention some other tools that we have in the works that eventually we're planning to apply similar strategies to. So this takes us back to source property estimation, which happens way after the open public alert, which is done as fast as possible. So this is over the scale of days or weeks or months. We will try to infer the accurate source properties where, again, we're assuming that the noise, so the residual of the data minus the source model, is consistent with Gaussian noise. Where it's not, right now, human beings, so experts that are trained up to do this, will take a look at a spectrogram that looks like this. So this is time and frequency. They'll find a big glitch or a small glitch or whatever glitches are there, and they will by hand, based on what their human eyes are seeing, enter this time and frequency range of the glitches that are in the data. So this manual identification, so this is for a very famous example. This is actually a glitch that happened almost right on top of this neutron star merger event in 2017. This is the LIGO-Livingston data. But this human expert approach can introduce a lot of issues in terms of consistency, reproducibility, and also people just making slightly different choices or maybe missing particular glitches. So in order to address this, we're modifying the GravitySpy convolutional neural network decision tree, which is based on GravitySpy. And what GSpyNetTree does, it is currently running in production as a glitch identification tool. So it will intake as part of our event validation process, candidate events, and it's capable of identifying at the same time a gravitational wave, which we can ignore because we've already found it, and some kind of a glitch. So this is a multi-class classifier that can issue results for multiple types of objects at the same time. That has been performing very, very well on LIGO data for 04, and we're currently working on updating it to include Virgo. And this is a series of studies that have been led by Sofia Alvarez-Lopez, who's now a graduate student at MIT. And the idea here is to take this algorithm and automate it such that it's now doing the work for us, for our human experts, and identifying not only that there is a glitch, but roughly where it is in time and frequency. So Mervyn Chan, a postdoc here at UBC, has also been leading this effort, and we've dubbed it GSpyNetTree S for segmentation model. And just to give you a sense of how it's performing right now, so here's a ground truth with a few features in the data that have been labeled by hand by a human expert. We've got a gravitational wave, we've got the time limits and the frequency limits, we've got a blip glitch, and we've also got this low frequency line. And then here is what GSpyNetTree S thinks is in the data. So it's got 100% probability that there is an object here at the time for all three real objects, and it's doing a great job right now of very nearly nailing where the time frequency boxes should be based on where the human thought they were. So we're pretty close to producing an algorithm that would be able to automatically and also fully reproducibly identify all the glitches for our event candidates. And through this process, we have learned the importance and the best practice of a very well understood training set. So I've showed you this glitch once before. So this is the LIGO-Livingston data for the 170817 detection with this great big loud screaming glitch in it. So this is an example of where it's very easy to see for a human or a machine where a glitch is present in the data. Here's another example, and there is a glitch in this data. It's not here, it's actually here, right on top of the signal. And the only reason we know this is because it happens to be coincidence with a very good witness, which is an accelerometer that captured a camera shutter snapping closed at exactly the same time. So here are cases where if I were a human, let's say labeling sets for a training set, this is something that I would miss, and it's also a corner case that we have a lot of trouble dealing with. So this motivates the needs for us to be very, very sure what exactly is in the data. You can never, if you're using real data, either turn off the universe with gravitational waves or turn off the Earth in terms of making glitches. So towards this end, we've been thinking a lot about making this fully simulated data set that's as realistic as possible. So we've been looking to models of glitches that can be described with physical parameters. So here's a study that was led by Ruxandra Bondarescu, who's now in Barcelona, for 3 common types of short duration glitches in LIGO and Virgo detectors that can be described by a very simple set of physical parameters. So the amplitude, the phase, the frequency, and then also the bandwidth. And we're also thinking about light scattering. So these are the same kinds of glitches that you saw before that we tend to see a higher rate of if there's elevated ground motion. And here you can describe these with a fairly simple model that's related to the speed at which the surface that's reflecting the light is moving and how many times that light is reflecting. So we've got 2 physical sets of models, the second one led by Rhiannon Udall at Caltech, that we can now incorporate in this software we call Glitch Pop, where you've got simulated Gaussian noise, simulated gravitational waves, both of which we've had for a long time for a variety of through a variety of different codes, and now also incorporating this third element, which is this simulated glitch population. So you can produce an end-to-end time series with a population of all these elements that can be distributed however you choose, a Poissonian distribution or let's say a regular and time distribution that can be used for testing these algorithms, especially in some of these really tricky corner cases where you've got overlap that might not otherwise be obvious even to a human expert eye. All right, so I think this is where I'll leave you. This is something we're really excited about. If you're in the market for building these kinds of populations for something that you're working on, please feel free to go ahead and make use of that. All right, and thank you so much. I'm very happy to take any questions.
Great, Jess. Thanks very much for that. That was very interesting. Let me start the questions if there are any. But the more recent glitch detection, GWSkyNet S, was that? I think it's called.
We've got many G's and S's.
Yeah.
Segmentation is GSpyNetTree. Yes, that's right.
Yeah, that's the one. So I mean, how much in real time is that in operation? In terms of what's the latency that you could actually apply that to the real-time data stream that you're getting from LIGO?
That is an excellent question. So I should emphasize that this is currently still a prototype. So
Yeah.
a GSpyNetTree is running on the order of tens of seconds, which is perfectly fine latency for what we call offline validation. So this is a step that happens as part of the catalog process. So this would be one step before source property estimation. So it doesn't actually inform the open public alerts. It's not happening in that low latency space of the real-time alerts. But for the segmentation, to answer your question, the last I spoke with Mervyn, I think the model, it certainly took a lot longer to train, but I think the model could produce a segmented image on the order of a few seconds, possibly less.
Great. Okay. Michael has a question.
Sure. Thanks, Jess. Nice talk. Maybe do you want to talk a little bit about your experience with, getting some of these ML models in production, both in low latency as well as sort of interacting with some of the broader software ecosystems? Because I suspect that those experiences will, be of interest to some of this broader group. I don't know if you want to talk a little bit about that.
Absolutely. And I actually had a couple of slides to that effect that I had cut for time, but maybe let me just go back and grab those. But it's an excellent question. So I think I definitely don't want to minimize the amount of time that we spent on those particular steps. So let me share this. Okay, so yes, so here's the timeline. So when I first showed the paper that Miriam led with the prototype, so this was in 2021 that it was published. So it's been yeah, about 4 years after we had a working prototype, more than a year and a half after this fairly intensive process that LIGO-Virgo-KAGRA as a collaboration undergoes to review pipelines, especially pipelines that are issuing information in low latency, where the stakes are higher and the performance has to be held to a higher standard. And then we also had a number of other steps after this process was finished, after we had gotten all of the various approvals and the documentation was public and we were more or less ready to go, I think it's maybe worth emphasizing that we have tried many more algorithms through summer projects and exploratory works than the two that I've highlighted in this talk, which have made it all the way through to production, which is a very labor-intensive process, exactly as you said, fitting in within the broader software ecosystem, making sure that they're well maintained, that also that they're performing well in the kinds of corner cases where you might expect, let's say for GSpyNetTree, we had this issue in earlier observing runs where candidates were coming in offset by, up to about a second. And if you offset the image, and we had an original version of the algorithm that was not robust to that, and we worked really hard to augment the data to make it robust to these kinds of corner cases. So yes, there's a lot of time and attention that goes into trying to ensure that the algorithm is going to behave in a way that's robust to as many things as you can think of, and that you can at least understand the parameter space where either you don't know what it's going to do, or you can predict how it might potentially not issue an answer that's correct. So yes, GWSkyNet and GSpyNetTree both perform very, very well, but you notice I'll make statements like, for GSpyNetTree on LIGO data, because this is something that we understand that it's not well trained enough yet on Virgo. So I'm happy to say more. I'll also show the next slide, which is the cake that we got to make. This is showing the label, the very first open public alert that carried automatically produced GWSkyNet information with it. And this is Mervyn, who, yes, again, worked for years and years and years to make that possible.
Great. Do we have any more questions? Not seeing any other hands up. Okay, Jess, great. Thank you very much again for your time. And thanks everyone for connecting. Next month's A3D3 seminar will be on March 10th, and it'll be Yonglin Feng from Texas Tech. Okay, thanks everyone.
Yeah, thanks everybody.